Good morning again. Welcome to Chem 100 on our Wednesday morning class. Today we're going to be finishing up our packet for this week dealing with chemical reactions and equations. On Monday we talked about balancing chemical equations, writing chemical equations from reactions. Today we're going to talk about the energy involved in chemical reactions and how we express that and how we use that to kind of think about what's going on. So first, as a little bit of review, we have some signs that a chemical reaction has occurred, and we've talked about this before. What shows a chemical change? Chemical reaction, chemical change. Talking about the same types of processes. So color change is one. Evolution of gas or smell, which is the smell is usually a gas also, or something volatile at least. Precipitation. You saw well, half of you saw that in lab last week, and half of you will see it today, where you add some clear solutions together and then you form a solid, which sometimes just makes it look cloudy. Sometimes you can actually see the little bits of solid forming. And then temperature change, like a spontaneous temperature change. So where you, not where you're putting heat in to boil something, but where you're mixing things at room temperature and they all of a sudden get really cold or get really hot. Now there is a, these aren't, as we've said before, these aren't totally 100% always true. For instance, you can have a temperature change when you put something in solution, either cold or hot, which we know making a solution is a mixture. That's not really a chemical change. You can have a color change with mixtures also if you mix things that are different colors. But kind of these unexpected or really obvious color changes or temperature changes that are not expected based on what's being combined is what we're talking about here. So when, and you can ignore this because we haven't talked about moles yet. So we're going to skip that. I should have deleted that. Get to that later. So now let's talk about how we measure these energy changes, because when we talk about things getting hot or cold, what we're really talking about is the transfer of energy via heat. So just a couple definitions. Energy means the ability to do work on something else. So if you raise a book up high, you have done work on the book. You've taken it from a lower energy state and put it into a higher energy state. So you've transferred energy from yourself to the book. And that is, so you had the energy, you did work on the book. Now the book has the energy. We can talk about two types of energy, which you probably heard before: kinetic energy and potential energy. So kinetic energy is the energy that something has when it's moving, and the potential energy is the stored energy when it is not. In chemistry, and for us, what we care about is the potential energy is the bonds. So the energy between, we talked about how when atoms bond, they become more stable because of the covalent bonding, also ionic bonding. And because that makes it more stable, that means there's potential energy in that bond. And so when we break and form bonds, we are transferring energy into or out of the chemicals. And we measure that energy with two main units, either joules or calories. We have to be a little bit careful here. I'm going to zoom in so you can see this really well. Joules usually, whatever, it's just a J, fine. Calories gets a little tricky because we use that term in our everyday life when we talk about food calories. But the food calories we talk about are not quite the same. The food calories are actually kilocalories, or also known as capital C calories. And that's especially confusing because C is a letter that basically looks the same if it's lowercase or uppercase. So if you make your C a little bit too big, all of a sudden you're off by 1,000. So just to answer this question here, there are 1,000 little c calories in one big C calorie. And a calorie is defined as the amount of energy it takes to raise 1 gram of water 1 degree C, a little c calorie. So when you look at the calories in your food, if a snack has 100 calories in it, that's actually 100,000 of these little c calories. And so we can do some of these conversions by either multiplying or dividing. So if we want to know how many capital C calories are in 8,368 joules, First, we want to take this into kilojoules. So that equals 8.368 kilojoules. And then we can divide by 4.184 to get calories. So the answer is 2. 2 calories in 8.368 kilojoules. Don't worry so much about these types of conversions right now, because our next chapter is more about how to do this systematically, and I think it'll make more sense. For now, just focus on the conceptual aspects of energy. Okay. Temperature versus heat. So temperature is not a measure of heat. Temperature is a measure of how fast the particles that make up matter are moving, and they could be just oscillating like in a solid, or they could be actually moving around like in a gas, across distances. Heat describes a transfer of energy. So if there was energy in one place and now there's energy somewhere else and no work was done, that's heat, the exchange of that energy. And you can think about this based on units. That temperature is measured in the units that we've always talked about: degrees Celsius, degrees Fahrenheit, kelvins. Heat is measured in joules or calories, just like energy, because heat is a measure of transfer of energy. So when heat goes into a system or goes into a, let's say, mixture of chemicals, that's called an endothermic reaction. Heat going in, N, right? Enters, N. Where this is sometimes tricky is because we experience something that seems like the opposite. So if you do a reaction and it's an endothermic reaction where heat is entering the chemical reaction, that means that it's going to get cold. Because what it's doing is it's pulling in heat from the outside. And that can sometimes get messed up in our brain or mixed up in our brain because we think, oh, it's getting cold, it's losing energy. But no, it's getting cold, it's gaining energy, and it feels cold from the outside because it's sucking that energy in. So if you touch the side of it, it feels cold because it's sucking the energy in from your hand. The opposite of that is an exothermic reaction, where the energy is being given off, and that feels hot, like a fire, for example, is an exothermic reaction, because the energy from the chemical bonds that are undergoing that combustion is being given off out of the reaction system. All right, so endothermic, the heat is going into the chemicals. Exothermic, the heat is coming out of the chemicals. So to illustrate that, we were going to look at something called a heating curve for water. So this is what's happening as water is heating up. And so the axes here, on the x-axis, we've got heat added. So as we move from left to right, we're adding more and more heat. And then the y-axis is temperature. So you would think, in general, like if you're just heating something, as you add more heat, the temperature increases. And that's what we see on these diagonal slopes. So let's take a look at liquid water. We start anywhere on here, right? Let's say we start here. And we add heat. As we add heat, the temperature of the water increases. Makes sense, right? You add heat, you put your water on the stove, you turn on the burner, you add heat, and the water gets hotter, right? Okay, so then what happens at these inflection points where it actually levels out? Well, this is what we call our state changes. So as you get to the boiling point, which we know for water is 100 degrees C, now you're adding heat, but you're not changing the temperature. And that's because that heat is going not to change the temperature of the water, but to break up those intermolecular forces that the water that attracts the water molecules to each other. Again, we'll get into that in I think the next chapter or maybe 2 chapters, what those forces are. But we're breaking those water molecules, we're separating the molecules apart from each other so that they can become gas. So in terms of exothermic and endothermic, we would say that melting and boiling are endothermic because we're adding heat to make those state changes happen. And then the opposite, if we're cooling water, we get steam and then it condenses to form liquid water, and then the water freezes to form ice. Now the heat is coming out without a temperature change. So we would say that those state changes, condensation and freezing, are exothermic. And that sometimes is really confusing because you think of, for example, water becoming ice, you think of that as like freezing, as being really cold. But when water freezes to ice, it actually gives off energy. Exothermic process. So you can kind of go through that again on your own and make sure that you have that straight. All right. And so now let's look at this energy transfer. We're going to use a couple different terms and variables. So we talked about heat. Heat is represented by the variable Q in physics and chemistry. And we're also going to talk about something called delta H, which is called enthalpy, which is related to heat in a chemical reaction. It's a little bit different, but we're going to use them roughly interchangeably. But to be totally correct, we say that when the enthalpy is greater than 0, that's when the heat is going into the reaction, and that's an endothermic process. Excuse me. And the opposite is exothermic. So delta H, or the enthalpy, is below 0. It's negative numbers when the heat is coming out, and then it's positive numbers when the heat is going in. Another way we can look at this is through something called a reaction coordinate diagram, which is what these things are here, where we track the process of a chemical reaction and we think about what is happening to the energy. And we're going to use these for a couple different purposes. So let's take a minute to look at this. So in this type of a graph, the y, and I should label this for us here, called a reaction coordinate diagram. And the x-axis shows the progress of the reaction, which means reactants going to products. So we talked about those definitions last time. The reactants on the left, the products on the right. So as we go from reactants on the left to products on the right, what happens to the energy? So we would say in this particular example, our reactants are here in energy. This is their potential energy level where they start. So if you just had those chemicals, that's how much energy is in those bonds. And then the products also have their own energy level here when the reaction is done. So at the beginning, we're at this energy level. At the end, we're at this energy level. Because we went up in energy, that means that heat was absorbed during this reaction, and this is therefore an endothermic reaction. So this reaction coordinate diagram describes an endothermic reaction. You'll also sometimes see, instead of flat lines here, it'll be like a curve. But same idea for us, same thing. So the products kind of sit in like a well or a low spot instead of a flat spot. But same thing, I'm just saying you'll see them in looking a little bit different sometimes. All right, so there's a overall energy change during the reaction, and that is what we call this delta H. Because it went from low to high, that's a positive change. And so going back up to our example here, a positive change means delta H greater than 0, and therefore endothermic reaction. That reaction is taking in energy. We're going to talk about this hump in the middle in a second. But let's look at the other, at another version of this, right here, where we have an exothermic reaction. And you can see how the reaction and reactants and product energy levels are flipped. So we start at higher energy with the reactants, and then we drop to lower energy for the products. Since the heat went down, that's a negative delta H, and therefore that is an exothermic reaction. That energy left the chemicals. All right. So now let's look at this hump in the middle. So you'll notice both of these. Sorry. Okay. Both of these graphs have this this hump in the middle, and that's known as the activation energy, or energy of activation. So when you have chemicals like reactants and products, like imagine something like fossil fuels, right? Things that you hydrocarbons, things that burn really easily, fuels. Those are we know those are exothermic reactions because when we burn them, when you get them started, they give off a whole lot of energy. But That means that those reactants, the fuels, are at higher energy than the products. So why don't they just spontaneously release that energy to become more stable? And the answer is that that reaction can't occur unless some energy is put into the system to get it started. And that's known as the activation energy. And that's why a fuel just sits there and is perfectly fine sitting there until it gets a spark or a flame or sometimes a really hot torch or something like that. It needs some energy put in to get it going and to make the reaction proceed, and that's known as the activation energy. So these reaction coordinate diagrams will always have this type of a shape: reactants, some sort of an activation energy, and then products, but what might change is the relative levels of the different parts of the diagram. These are also one-step reactions. If you had multiple steps in a reaction, you would have multiple humps. All right. So let's take a look at how we figure out which direction energy is going in a given scenario. So let's say your hand gets cold when you touch ice. And we have to label a system and then label it as exothermic and endothermic. And the reason we have to pick a system is because this is an arbitrary decision. And depending on what we pick, the answer is going to be opposite. So there are basically two things in this situation. There's your hand and there's ice. So do we want the system to be your hand and ice? There's no right answer here. We pick either one. So let's do both. Let's say the system is your hand. So if we assume that your hand is the system, is this endo or exo, which means is the energy flowing into your hand or out of your hand? Well, your hand is getting cold, right? So that means the energy is coming out. So that would be exo. But let's say instead we define the system as the ice. Well, now the question is the energy going into the ice or out of the ice? So if your hand is getting cold when you touch the ice, that means that the energy is going from your hand to the ice. So that means that the heat or the energy is going into the ice. And that makes it endo. You see how that works? Depending on which you pick as your system, meaning like the thing that you're focusing on, you're going to have the opposite answer of where the energy is going. And there's not a right or wrong way to pick a system. We just have to be consistent when we make that decision. When we talk about a chemical reaction, then we're always talking about the actual chemicals as the system. So let's jump to C here. Ice cream melts. Well, now we don't have a whole lot of choice here, right? The system is the ice cream. And if it's melting, does that mean that energy is going into it or coming out? Well, melting is an endothermic process. We need to add heat to get it to melt. So that is endo. All right, and then to bring in a chemistry example, this last one here. The system, in this case, is going to be the chemicals. So two chemicals mixing in a beaker give off heat, and this one really just tells you the answer here. They give off the heat, and so that is exothermic based on the chemicals. Now, if we took the system as being the beaker, then it would be endothermic because the beaker is getting hotter. The beaker is receiving that heat. And so that's why we don't do that. Same thing with even like the solvent, whatever the water or something, whatever's not being involved in the reaction. Those are all known as the surroundings. We want to focus on the chemicals as the system and think about, is the energy going into those chemicals or coming out? All right. Moving on, let's look at rates of reaction. So here we're getting back to this activation energy. And I don't actually love that example, so I'm going to skip it. Let's say we have a reaction coordinate diagram like this. The red is, we'll say, the original activation energy. The original activation energy for the reaction is this, which means that if we want to do this reaction, go from reactants and products, we have to put in this much energy. And maybe that's a lot of energy. In a lot of processes, it is, and it is a barrier to actually getting that reaction done. So there are various ways to reduce the activation energy of a reaction, and one of the best is to use a catalyst. A catalyst is something that you add to a reaction, and it reduces the activation energy by allowing the reaction to proceed by a different mechanism. And it's not itself used up in the reaction. So it stays basically around, and although it can be damaged in the reaction, I suppose, but it reduces that activation energy, which speeds up the reaction. So a catalyst decreases the energy of activation and increases the rate of reaction and is not used up during the reaction. And that is one way to lower activation energy. So one really important class of catalysts are the enzymes, which are proteins in living things that act as catalysts to do reactions that otherwise would be really high activation energy. So something that might not work in your body without your body being at a much, much higher temperature, an unlivable temperature. But because of the enzyme, that can act as a catalyst and have that reaction take place at a much lower temperature. And when we get into proteins later in the semester, we will talk about how those enzymes work as catalysts. Build some of them too. There are some other things that affect the rate of a reaction. The concentration of reactants, the surface area of reactants if they're solids, and the temperature of the reaction. So let's see if we can guess how these would work. If you increase the concentration of reactants, let's see what's happening in that container. So that means there's more reactants, there's more molecules in the same volume. And what that means is they're going to bump into each other a lot more often. They're going to have a lot more collisions. And that's also going to increase the rate of reaction. If we increase the surface area, so we increase the concentration, we increase the rate. We increase the surface area of reactants. If they're solids, we have the same thing. If you imagine having like a ball of metal, it's only going to be able to react on the outside of that ball. And so that's going to be relatively slow. It's going to have a higher activation energy to get in there. But if we grind that all up and have a very fine powder, we have a much higher surface area. And so that speeds up the reaction or lowers the activation energy. We can use those terms, speeding up the reaction, lowering the activation energy, interchangeably. The activation energy applies directly to the speed of the reaction or the rate of the reaction. So in a similar way, increased surface area increases the rate of the reaction. If we increase the temperature, we make the molecules move faster, make the atoms and molecules move faster, which has a similar effect, especially as the concentration. If they're moving faster, they're going to bump into each other more often, and that's when you have that reaction. And so that's also increasing the rate. So these all increase the rate. They don't increase the surface or they don't necessarily increase the decrease the activation energy. So I misspoke a little bit there. If you increase the temperature, for example, what you're really doing is you're just making sure that there is plenty of energy to get over that activation energy, and you're increasing the rate. It's really only when you're changing the reaction with a catalyst that you're changing the activation energy of that reaction. All right, and then the final thing we're going to talk about in this section is equilibrium and Le Chatelier's principle. So we drew reactions or our equations in the beginning, like this first example here: 2SO2 plus O2 yields 2SO3. But all reactions also have a reverse counterpart. So reactions can go forward, but they can also go backwards, which is depicted in the second one here. So 2SO3 goes to 2SO2 plus O2. That's the opposite or the backwards reaction from the first version. So another way we can write that is to just have a double-sided arrow. And usually, I think this isn't issue with how this was typed, but usually we actually use 2 arrows because that double-headed arrow means something else in chemistry. So it's a little bit better if we can actually use 2 arrows. But if you see that, that's what that means. So the reaction is really always going back and forth. And at some point, it reaches what we call equilibrium, where the reverse and the forward reaction are going at the same rate. And so you have some sort of balance there. So we're no longer really changing concentrations of each. We're really balancing it out. And I think a good way to think about this, I don't know if I put the picture in here or not, is with water, because it makes more sense physically. So let's imagine we have 3 tanks of water. And they're connected by pipes. I don't know why I drew them at an angle. Let me do that. All right. 3 tanks of water connected by pipes. If we just only fill up number 1, bin number 1, pot number 1, whatever we want to call it, tank number 1, what happens? Well, the water is going to flow out into number 2, right? And if we have water also in number 3, that's also going to try to go this way. And depending on the amounts of each, at some point, I mean, very quickly, it's going to all kind of balance out. We're going to have the same level of water in all 3 tanks. All right, so now what happens if we take out, if we put more water in tank 1? Well, it's going to flow over here and make this fill up more. What happens if we hold on, I did this wrong. Sorry. Only 2 tanks, not 3. We're going to make this easier. So if we put some water in tank 1, it flows into tank 2 until these are equal, right? They're going to equal their levels. Then if we put more water in tank 1, it's going to flow over and push this level up more, right? If we put more water in tank 2, it's going to be the opposite. We can also think about what happens if we take some out. What if we have a bucket and we remove some water from number 2? Then more is going to flow in from number 1. This is going to get lower and it's going to re-equalize. So the same thing happens with chemical reactions if we think about reactants and products. So going back up to our reaction here. If we start with our reactants, they're going to make the products, but then the products are also going to go backwards toward the reactants. So at some point, that's what got me confused, this triple picture here. So at some point, there's an equilibrium where we have some reactants, we have some products together, and they're no longer changing. But if we move the amount, or if we change the amount of either reactants or products, we're going to change what's in there. So if we can remove products by, let's say, evaporating a gas or releasing a gas, then we're going to move and create more of those products from the reactants. So if the equilibrium is disrupted, then it will kind of remake what's in there. I'm sorry, I'm tripping all over my words this morning. There are some better pictures and descriptions of this in the linked textbook, the online textbook, so make sure you read through that if this got a little bit confusing here. We're not going to do any calculations or anything with this. You can, if you go on and take more chemistry, you can figure out exactly how much of each thing is going to be made at different conditions. But we're just interested in this idea, this concept of equilibrium, that when we remove molecules from one side of the equation, the other side is going to compensate and kind of like refill them. All right, so that's chemical reactions and equations. I am not going to post a separate homework on Blackboard this week because there's so much to do in this particular packet, especially with the balancing equations. So you can just do the packet for this week. We will have a quiz pop up probably tomorrow, so you can work on that over the weekend. And I will see you later. Oh, I will put this on Blackboard, but I have a thing. There will be no live stream on Monday night. We're going to do it Tuesday. I have to find a time that I can do it. Probably Tuesday sometime instead. So I will see you then. And I'll see half of you at lab today. Bye.